FloEFD for NX can be used in a fully integrated workflow with Simcenter 3D for thermal, mechanical, and thermo-mechanical studies. This workflow video will outline the steps of such an approach. A full authority digital engine control or FATIC unit is modeled in Simcenter FloEFD for NX mounted on an engine nacelle. Starting with an empty unit, a populated PCB is imported to be placed inside it. An ODB++ archive exported from Expedition PCB is imported into the EDA bridge interfacing window for thermal model preparation. Thermally critical components are unfiltered and considered for a thermal simulation. In this case, all those components that are greater than 0.6 mm in height and 3 mm in length. By default, all components are unpowered. By importing a power list, these powers can be set automatically. The PCB is set to be modeled in a compact form, a lumped object with appropriate orthotropic thermal conductivity values. The thermal representation of the PCB is transferred to Simcenter FloEFD and located in the FATIC enclosure. A fixed temperature boundary condition of 90 degrees C is set on the housing. A full 3D CFD thermal simulation in Simcenter FloEFD predicts operating component temperatures as well as PCB temperatures. Natural convection airflow distribution within the FATIC enclosure is also predicted. The FloEFD results are unloaded and the Simcenter 3D pre-post interface started directly on the same model geometry without leaving the Siemens NX session. A finite element mesh is applied to the same model geometry. The casing and the bracket are using automatic mid-surface 2D meshing technology, and the electronics components are meshed using a combination of 2.5D and 3D meshing approaches. A dynamic analysis is conducted with a sinusoidal excitation of 20 Hz from the center. After the solve, we can directly open the results on the same user interface and define post-processing activities. At this stage, we are able to define the mechanical stress on the bracket and the acceleration on electronics components. Transient von Mises stresses are predicted and shown in the support brackets on the PCB. The analysis identifies where the increased stresses are located so that remedial action can be taken. A more detailed model of the thermally critical QFN component is created using Simcenter Package Creator. Parametrically specified using a default JEDEC outline, a 3D model is created automatically. The number of bond wires can be parametrically modified. Though in this case the bond wires are excluded from the model due to their thermal insignificance. The detailed QFN model is exported to FloEFD, then EDA bridge is used to define a thermal territory, a region of the PCB local to the QFN where an explicit geometric representation of the PCB routing is defined. This thermal territory region extends through all layers of the PCB. The detailed QFN and PCB thermal territory model is isolated from the system-level FloEFD model with boundary conditions applied to the periphery of the zoom-in model. The QFN power dissipation of 0.8 watts is cycled with a period of 2 seconds and a transient thermal simulation conducted. Sufficient power cycles are simulated until such time as the thermal response becomes periodic. Once this is achieved, the full transient 3D temperature fields of the final cycle response are exported to the file system and converted into a format for direct seamless import into Simcenter 3D. The FloEFD simulation considered all layers in the thermal territory as explicitly represented, which provided the most accurate temperature prediction. For the thermomechanical simulation, the top layer will be considered along with the relevant QFN structure to do the thermomechanical analysis of the solder joint. The interface between the component are solved with the contact type gluing. 3D temperature fields as predicted by FloEFD are seamlessly mapped onto the equivalent finite element mesh necessary for thermomechanical simulation. Once those temperatures are set as load boundary conditions, then a thermomechanical simulation can identify areas of undue strain and therefore identify areas that may benefit from remedial design actions so as to minimize that strain and therefore minimize risk of reliability-based failure. After the solve, we can directly open the results on the same user interface and define post-processing activities. At this stage, we were able to perform a thermomechanical analysis of a solder joint where we can deduce the temperature, the stress, and the strain between the solder and the leads. The transient variation of the strain at the selected point of the largest strain is plotted throughout the cycle. The tightly coupled workflow presented, where Simcenter FloEFD and Simcenter 3D are used together for thermal, fluid, mechanical, and thermomechanical analysis, will enable you to quickly and accurately achieve a design-compliant solution for your electronics assemblies.